we want to explore this one idea here about why does a p orbital have a higher energy than s orbital, and we're talking about multi-electron atoms. So to really explain this idea, we need to look at shielding, we need to look at something called effective nuclear charge, and then how do those change the potential energy of these two orbitals. In a hydrogen atom, then there is the n equals 1 energy level, and we have this orbital, and when n equals 2, we have a s orbital and we have the 3 p orbitals. Well, we have exactly the same thing in all of the other atoms as well. So this picture works for the location of the electrons in hydrogen and all the other atoms. But this is also the picture for the energy of the orbitals in a hydrogen atom. But energy for everybody else, and we're talking about potential energy, has this sort of a picture where the 2p orbital is a little bit higher energy than the 2s orbital. And that's what we want to explore. In this picture here, we can see that we have lithium. Now for lithium atom, we can say, well, let's put in some electrons. So over here on the far right, I have lithium and I have a 1 electron in its 1s orbital, and I can put another electron in its 1s orbital, and the third electron would be somewhere out here, either in the 2s or the 2p. The ground state would put it in the 2s. But what I'm really concerned about is the fact that we have 2 electrons down here in the 1s orbital. So on our picture here in the middle, here is an electron, and here's our electron cloud. This is our 1s orbital, and this electron could be all over the place. This is our 2s or 2p electron, could be all over. Now if it turns out if it has a chance to be really close to the nucleus, then it's going to feel a +3 charge. So that's like over here on this picture. It says, the shielded charge, if it's really close, if there's 0 distance from the nucleus, it feels all 3 protons. But the farther you get out and the farther you get out, okay, the less that it's going to feel of that +3 because it has negative electrons in the way. So these electrons, these 1s electrons, we say that those are going to shield the outer electron from that +3 charge. Now by the time it gets any kind of distance away, then we can see that now it just basically feels a +1 charge because there's +3 protons in the nucleus, 2 negative electrons in the 1s orbital, so this outer electron is basically going to have an effective nuclear charge of 1. Now let's put that together. Here we have our picture, and we can say that if you're really close to the nucleus, then you get a +3 charge. If you're farther from the nucleus, you get a +1 charge, effective nuclear charge. And we have 2p orbitals, and we have 2s orbitals. Well, what do they look like? They have a different distribution. So we go back to our idea of the psi squared, and for a 2s orbital, the psi squared picture, mathematically it tells us that there's a really good chance of finding the electron near the nucleus, but at some distance, then we have a node, and we have more chance of finding an electron again farther out. For a 2p orbital, it has a different picture. Right near the nucleus, there's 0 chance of finding the electron, and then we have a chance of finding it and it drops off again. So this beginning should be right down to 0. Now, putting these ideas together, we say over here, okay, here's a good chance of finding the electron. And when those electrons, I said that wrong. Over here is a good chance of feeling a positive charge greater than 1, so you feel a +2 or +3 effective nuclear charge. So for a 1s orbital, this electrons that get to spend their time close to the nucleus, then they get to feel more than a +1 charge, quite a bit of the time. Where for that same idea here, for a 2p orbital, then they spend their time on the average, farther, the distribution, they spend their time electron farther from the nucleus, so they don't get to feel that nice +1, anything +2 or +3 charge. So what happens is the 2s orbital, okay, because the electrons spend their time close to a high positive charge, they're held more tightly to the nucleus. And if we wanted to take that electron and remove it, we would have to add a lot of energy. So if we kind of remember what we used to do with the hydrogen atom, we said, let's say n equals infinity up here, and this would be 0 energy, the energy if that electron completely took off. But if we were to do that from the 2p orbital, okay, 2p orbital, the electrons, here do not get to feel a very large effective nuclear charge, so they're not held on quite so tightly. So we can see here that these electrons in this level would not require as much energy to be removed. Now, if it requires more energy to be removed, then that means you are lower potential energy. So that's our picture, the potential energy graph. The 2s is a lower potential energy because it is more stable, held to the nucleus because it has a greater nuclear charge, effective nuclear charge, and the p's are higher because they have a little bit less nuclear charge. Now this is a picture from our book which is trying to do exactly the same thing. So we're saying that here is the s orbital, and the s orbital, you get a lot of chance here for that electron near the nucleus, and the p orbital, not so much. Here's the p orbital. Okay, same thing, not very much close to the nucleus. So we get back to our picture and we say, well, for hydrogen, then there's no shielding at all, because the electron can either be in the 1s orbital, or it could be in the 2s orbital, or in the 2p orbital. But if it is here in the 2s orbital or in the 2p orbital, there's no electrons in the 1s orbital, so you don't have any kind of shielding. So a 2s orbital, 2p orbital makes no difference. You have the same energy for both of those. But when you get to the 2s and the 2p, for multi-electron atoms, then it makes a big difference. So the 2s orbitals have a chance to get a large effective nuclear charge, so they are lower energy, and the 2p orbitals have less effective nuclear charge, so they get a higher energy. And that's kind of the story.